Okay. All right, so last time we solved the secular equation. We had some expressions. We were trying to find the coefficients. So we had looked at our basis functions. And let's say we were looking at MO, or molecular orbital number 1. We had some coefficient times 2p on carbon 1 plus alpha 2, like this, 2p coefficient on carbon number 2, excuse me, p orbital on carbon number 2. And 2p carbon number 3. What we want to do is we want to find the contribution of each of these orbitals to this MO. A funny thing in this historical account of Roald Hoffmann is he said he never really cared about that when he was doing it. He just cared about doing the calculation and getting those results. And it wasn't until he started drawing those out that he figured out a lot of things. So we wished he would have visually represented that way sooner. And I also agree with him. One other thing he said is he wished he didn't work so hard and fast. He wished he would have taken his time on some stuff. And I also feel very similar in some cases. Anyways, enough philosophical bullshit. We tried to find these A's. We looked at the secular equation. We determined 3 equations out of this. And we arrived last time at this. So we got some connection between A1 and A2. Is that correct? Okay. Now we're going to utilize our 3rd equation to get a connection between A2 and A3. In that 3rd equation, our first term was 0. Our second term was this, and our 3rd term that's what our equation was, right? You might have to do some multiplication through. If you look at this, though, you're going to end up with the exact same result, just with different coefficients. So how does A2 relate to A3 in this case? Or do you want to do the manipulation? Check out when we did this stuff. Yep, so instead of, this term was not 0, it was just this, but with an A1, right? Yep. There we go. Okay. So now we have this relationship between all the coefficients. Wave functions. Given wave functions, there's some requirements of them. Those who are in quantum and modern and those who have taken PChem, what do you know about requirements for wave functions? They have to have a couple of things. Normalized, that's what I'm looking for. They also have to be continuous functions, and you can only get one value for them, but must be normalized. Okay, so that normalization, what does normalize mean? Yeah, so all the probabilities over the range you're interested in add up to be 1. There's a couple of mathematical ways you can do that, but since we're bound that way, you end up getting these coefficients. Okay, so therefore, our MO number 1 looks like this. Okay, looking at this, which orbital contributes the most or has the most character to this orbital? The second one, because the coefficient's the biggest. Okay, that was for orbital number 1. How many other orbitals or MOs do we have? We got 3 in total. We got 2 more. You could do this exact same process for the other 2. I don't want to do it because it just eats up time, and it's just algebraic manipulation. But let's write out the equations for the others. So following a similar process, you end up at this result. Plus 0 minus and then we got I think I am. Yes. I know I'm just uncharacteristically quiet right now. Okay, after you guys get that all scrambled down, we're going to draw a picture. Okay, we had 3 energies, right? Or 3 solutions to our determinant. 1, 2, 3. Oops, we did orbital number 1, orbital number 2, orbital number 3, or MO, excuse me. We have determined some energies for these things. What was the energy for the bottom one? Alpha. Yep. What was the energy of this guy? Yep. And the top one? Okay. Now, these are linear combinations of atomic orbitals, and they tell you a lot about the molecule. They also tell you the contribution of each atom. And when you have sign changes, when the atomic orbitals switch in and out of phase. Most computational chemistry software packages, you can input this and they will give you nice pictures. You see that in PChem 2 where you look at WebMO, or I might have made you guys even do it in Gen Chem second semester, like one of the first couple of labs. Let's plot this out though by hand, utilizing the information we've just obtained. So we're going to have 3 pictures of this molecule. They're meant to be symmetric. That was shit. It's okay. All right. What color do you want me to draw the orbitals in? Let's do yellow. Okay, let's look at our first orbital. Does each element have a does each atom have a contribution? Yes. Do their signs change? No. So they should all be in the same phase. The other question is do they all have equal contributions? No. 1 and 2 have a similar contribution. So we should draw their p orbitals about the same size. And remember, in this theory, they don't mix or overlap all the way. Now, for carbon number 2, we said the contribution is larger. So what should we do with the p orbital? Yeah, make it bigger. Yep. And does it change sign or phase? If you look at the overlap, if they were permitted to overlap, what type of orbital would this be? Not hybridization. It'd be a bonding orbital, yep. It's going to be a pi bonding. Okay, we'll talk more about that too and give a refresher in a little bit. Orbital number 2. Let's look at its contributions. Okay, do any of these systems not contribute? Which one? Yep. That means, and then what do you notice about the signs for carbon number 1 and carbon number 2? What was that? Yeah, they're opposite. There's actually a node that gets introduced here, and then are they of the same magnitude? Yeah. So if I drew this one big this way, there's nothing on carbon number 2. What would I have to draw on carbon number 3? And can you be more explicit in that?
Shaded on top.
Yes. We're going to worry about that in a little bit. These are too far away to really have any impact on one another in terms of their overlap, but it just is what it is. Okay, what about the third MO? Well, does each atom have a contribution? Yeah. Okay, are there any equivalent contributions? Which ones? Yep, carbon 1 and carbon 3. So we should draw them about the same size. Carbon number 2 has a greater contribution, right? Let's draw that one bigger. Okay, now let's look at the signs. If I label this one that way, what do you notice between carbon 1 and carbon number 2? The sign has changed. There's a node in here. So we got to change that. And what do you notice between carbon number 2 and carbon number 3? Opposite signs, another sign change, and a new node. This overlap is completely destructive. This is an anti-bonding orbital. Okay. So this is where the organic chemists get all their knowledge. They've done Hückel calculations, and they know this is what the orbitals look like. And they've just gained a lot of experience from p-chemists telling them how it is. This is where I started to learn organic chemistry, was from calculating stuff. I just memorized shit until I started doing this stuff. And I learned way more from organic. This realm of chemistry is called physical organic. Okay, now let's go back to our picture of our allele though. We had that, or we could draw another resonance structure like this, right? How many pi electrons are in this system? Because that's what we're caring about. 2, 3. Let's start filling this thing. 1, 2, 3. What's a weird characteristic of alleles? They're radical, yeah. What's another weird characteristic? Where will that thing react? On the ends. Only on the ends. Why does it react only on the ends? If you have something that is electrophilic and it wants to steal electrons, it's going to go for the highest energy spot, right? There's no contribution from that center carbon. What about if you have something that's nucleophilic and wants to give up electrons? Where's it going to dump those electrons? Yeah, this guy. It's going to donate it there. There's only character on the ends. There is no character in the center. The center carbon can't participate in that type of bonding. That is why they only react on the ends.